Hi everyone, welcome back. Today we're going to be talking about electromagnetic flowmeters, mainly the working principles behind it, the advantages and disadvantages of this method to measurement, and the types of electromagnetic flowmeters available under the Emerson-Rosenau framework. The electromagnetic flowmeters work through the concept of Faraday's law of induction. Basically, there is a coil inside of the flowmeter. The current is applied to the wire coils that are located in the meter body, and this generates a magnetic field. When the magnetic field is cut, in this case with a conductive liquid passing through the tube, a voltage is generated. Now, the magnitude of the voltage induced is directly proportional to the velocity of the fluid. So, the greater the speed and the energy with which the water moves, the greater the voltage that is generated. You can see this illustrated in the chart on the bottom of the screen. There are electrodes located in the meter body, and these electrodes are connected to the transmitter. So the sensing electrode detects the voltage that is generated, and it then sends the signal to the transmitter, and the transmitter calculates the flow rate. There are some limitations to be considered before opting for an electromagnetic flowmeter. Firstly, you need a specific length of straight piping to ensure you have a uniform fluid velocity. An electromagnetic flowmeter needs a fluid flow profile that is regularly distributed throughout the pipe in order to have high accuracy measurements. So, the amount of straight piping required differs from manufacturer to manufacturer. In terms of Emerson-Rosenau, they recommend 5 pipe diameters upstream of the flowmeter and 2 pipe diameters downstream of the flowmeter. And as I mentioned before, this is required because pipe accessories such as tees, bends, and elbows will disrupt the regular fluid flow profile within the pipe. The other limitation is that electromagnetic flowmeters are not able to detect medium with fluid conductivity less than 5 microsiemens per cm. Again, this differs from manufacturer to manufacturer. 5 microsiemens per cm is the standard. There are several advantages to electromagnetic flowmeters. The first being that there are no moving parts or mechanical parts within the actual meter pipe. So your pressure loss is kept to a minimum. The other thing is that these magmeters are able to measure bidirectional flow because voltage is generated no matter which direction your fluid is flowing. Magmeters are also unaffected by variations in density and viscosity in your medium. This is why it can be used for high viscosity mediums such as slurries. When selecting an electromagnetic flowmeter, there are certain parameters that need to be known. The first being the medium conductivity. We've discussed why it's so important in the previous slides. Next, we need to know the line size, the flow rate, whether an integral or remote display is needed, the type of process connection needed, so the type of flange, and the temperature and pressure of the line. There are several types of electromagnetic flowmeters available under the Emerson-Rosenau range, the standard being the 8705 electromagnetic sensor. So this is a standard process sensor. It's available with flange connections in sizes up to 36 inches. Depending on the line you use, you can go up to 177 degrees Celsius with your process medium, but you'll need to have the standard medium conductivity at 5 microsiemens per cm. You can see similar specs with the 8711 sensor. However, this is a wafer-type sensor, so it is considered to be more economical, compact, and lightweight. It's only available in sizes up to 8 inches, but in terms of process temperature and medium conductivity, they have roughly the same specifications. And both of these sensors are compatible with either the 8732 transmitter or the 8712 transmitter. Now you may be wondering if the 8711 is touted to be a lightweight sensor, how lightweight is it when compared to the standard? Well, if you're looking at a 1.5-inch flowmeter, the 8705 sensor could weigh up to about 10 kilograms, whereas the wafer-type sensor, the 8711, will only go up to about 2 kilograms. So there's a pretty big difference in terms of weight between these two sensors. The 8750 W sensor, on the other hand, is a specialized sensor, whereas the application within which it can be used is rather limited, solely to be used for utility, waste, water, and water applications. So it's available in sizes up to 48 inches, but medium conductivity must be at least 100 microsiemens per cm. When measuring the flow of slurries with standard electromagnetic flowmeters, you can expect a lot of noise in your flow measurement signal. In order to overcome this, you have the Emerson-Rosenbaum NF sensor and HMA2 transmitter that has been specially designed for use in measuring flow of slurries, pulps, and any medium that has a high solid content. It's available in sizes up to 36 inches. You'll have noticed a similar model called the 8707 model. This is actually an obsolete model that was designed to fulfill the same purposes, but it has now been replaced by the MS sensor and 8782 transmitter. The limitation of this measurement method, however, is that your medium needs to have a conductivity of at least 50 microsiemens per cm. For sanitary applications, you can have the 8721 hygienic electromagnetic sensor. It's available only in sizes up to 4 inches, but it is suitable for cleaning plates and sterilization in place applications. What makes it sanitary is this threaded IDF fitting, so the International Dairy Federation authorized fitting. And in terms of weight, it's pretty similar to the wafer sensor. So if you have a DM40 8721 hygienic sensor, it'll only weigh about 2 to 3 kilograms. We also supply several other electromagnetic flowmeters in a wide variety of ranges. These differ in terms of sizes, temperatures, and accuracy, and even whether you want high-level or low-level alarm outputs. For more information, you can visit our website at sasengineering.lk. Thank you very much.